Hi guys, welcome back to my channel. And this is day 12 of the DSA bootcamp. I will be starting with CFG portal, and the problem of the day will be count the smaller elements. And today it was 19th July, and this question was asked in Google and coordination. Let's go to the problem. And the current strike of my coding strike was 333. Guess the number. And here comes the question, and this question having the difficulty category of hard, and the question said that given an integer array containing of non-negative integers, which means that it will be ranges 0 to positive infinity, and we have to count and return an array in the format of answer array, where individual answer of the particular index denote the number of smaller elements on its right side of an array. For example, here the given question array, and this particular 12, the particular index 12, having the smaller, how many smaller elements in present in the given array, we have to count, and we have to return their respective count on the respective index itself. We have to return that particular format of an array. Hope you got the question. And for example, if the given question is ascending order, we have to return nothing is smaller than nothing, right? So every time if it is following in as a sorting order, like ascending order, we can return default values of zeros, and every rightmost element will be zero because nothing element will be there. That is the edge case, and you have to communicate with an interval so that you get some appreciation and positive feedback. And expected time complexity and log and the auxiliary space was linear, and the size constraints are size 1 to 10 power 6, and particular elements ranges from 10 power 8. As you can see, company tax. Let's go to the notepad. Yep. Hope you see my notepad and the given question. And first of all, we have to communicate with an interview saying that we should not go towards the optimist approach. We have to communicate with an ruthless approach. That will be like pretty straightforward. As the question said, we have to find the smaller elements. So on the right side, we can use two loops and one outer loop for the each element. Please count the remaining elements whose have the smaller values, and count, please keep track of the count and assign back to the particular index itself and return the array. We are using two loops, one for the outer loop for the each individual index, and please go to the rest all right side of your current element, the value. Please check the less than value, and increase the track the count and assigning those values and written back. That's what the brute force approach simple. And time complexity is analog, and this code was written in C++. And case was we are taking this was we have to written format. No need to consider. If it is considered, we can consider that this is not an auxiliary space, and we can return that, and that's fine. The space complexity here is constant. This is wrong completely because the given question states that we have to return an array. We are not taking additional data structure. This is for storing an answer. So the constant here, and the expected approach is that we should use Fenwick trees, because why we are choosing Fenwick trees? Fenwick tree is having the property of finding out prefix sums of an input array within the range itself. And if there is any offline queries and we have to find the range sum of that, we have to use Fenwick trees. It's also known as binary index trees. And to count the smaller elements towards the right hand for every element in a given array. The implementation part is pretty straightforward. We have to compress the array because of 10 power 8 is not feasible to initialize one dimensional array. If you are using any language, you can't initialize an one dimensional array of 10 power 8. So that's the reason we should compress it. The compression techniques are very simple. We should using sorting and mapping. Mapping is in the sense means we are mapping respective value to the respective index. For the given question, we have 12 at 0th index. So we are mapping 12 with 0, and then similarly, and after mapping that, we can sort accordingly. That is one compression. After compression, we should calculate the count by traversing right to left traversing into the input array, and we are updating the Fenwick tree binary index and getting with the calculated value, counting all the incremented counts, and we will be storing in a resulted array. We are returning back. That's what the intuition and the algorithm. And let's go to the code itself, and then I will be try running a few examples to get very to stick into your head. Okay, and we are using a global array. This is an bit array, and we are using this given question itself. And as we said, 10 power 8 not able to initialize an one-dimensional array, so that we have to compress it. In order to do the compression technique, we are using pair data structure, which will store of pair. Pair indicates the value and the respective index itself. As you can see, we are initializing a new pair with the given value and the index, as you can see here, every pair. After that, we are sorting based on the value itself. Based on the first occurrence, we are sorting, so that we will be forming a sorted order of the values, and respective this will be followed in individual pair. After that, this is the frequency step to compress the every value to increase their respective index count. For example, if we found the particular value multiple times, we can increment the particular count, and then we can ascend back to the given question itself. And after compressing that, we can return the particular index itself. This is the formation of an binary index, which means that we are not using the original indexes. We compress the indexes to fit 10 power 6 only, not 10 power 8. Because as the question state, the constant, it the each element will be ranges 10 power 8. We can't create a 10 power 8 binary trees of array size. So in order to fit into 10 power 6, we are compromising the indexes. That's what the compression technique here. And we are assigning to the given question array itself, so that we can solve. And after that, we are taking an bit array. It called as binary index tree, which is also known as Fenwick tree. This is an auxiliary space. 10 power 6 we are taking to store all the bits and respect to prefix sum or prefix counting. Those values we are storing in each individual bits. And then this is the resultant array. We should not consider in an auxiliary space, and this will be considered in an auxiliary space order of n. And then the time complexity for iterating and updating will be n log n. We are traversing to right to left, as you can see, and minus 1 to 0. And every time we are getting the respective bit index value, and we are setting to our we are constructing, we are building our answer, and then we are updating the respective index to the we found one occurrence of this particular value, please update in your binary tree index. And after that, after doing all the operations, we can return the our constructed result, the expected output. And here comes the binary tree. This is more complicated, and you can see pair data structure was simple, and you can use standard also in C++, the pair, and Java we have intense utility of pair class. And here comes the update and get function. This is the main important, the crucial factor, like how we are updating. Updating is simple mechanism by using them, taking an index, and this is where the P indicates how many points we have to add into our binary tree, the particular index itself, so that the binary tree index will work in this manner. The structure will be fixed, and let me explain the binary tree index how it works. Here the given example where we are taking some values in an array and respect to indexes. Okay, and the binary tree index, like Fenwick tree, how it works is that whenever we are taking any value here, we take the two value which will be forming of binary value of 1 0. If we flip the rightmost set bits, so that we will get 0 0, which is nothing but 0. For one index, we have the parent of 0. That's what the indication in a bit. Bit indicates binary tree index. And for respect to this value will be 8, will be pointing towards 0. As you can see, 8 value index, bit index value will be pointing to 0. Like this, it will be formed. For example, let me solve for 11. 11 binary index will be 1011. If you flip the rightmost side bits, you will get 10. So 11th binary parent was 10. That's how the standard structure for BIT or a pen victory. This is fixed, and the inside this value will be differ. If you want the prefix sum within the range, you can use here, like in the update function. In the update function, if you are using the count for every occurrences, you can use one. If you want to update the prefix sum, you can pass the previous sum value, previous cumulated sum value. You can pass it so that it will be updated to the respective index. So the branch will be updated every time. Okay, and let's how to write those values. Let's define that. For example, here I took can reference from one of the famous there to show, and then how we are populating is that simple. We are taking the 7, the numerical decimal value. When we convert it into binary format, the first two occurrences will be stating that the starting range where we have to start the prefix sum, and the last component indicates the how many digits, how many elements we have to go for. For example, 2 power 2 square 4, 4 plus 2 is 6, which means that we are starting from 6th index and we are going up to 2 power 0, which means that one index we are going. So for index 7, the BIT 7, you can go to the respective 7. Here the 7, the value is 3, and we are going up to one index only, so that this range is nothing but 6 comma 6, and minus 3 will be the BIT value for the index 7. And for index 8, similarly, we are starting from 0, we are going up to the 8, which means that we are going up to 7. Calculating the sum, you can see, and we got 19, and ranges is this one. Similarly, for 11, 11 will be 2 power 8 plus 1, nothing but 2 power 8, 8 plus 1, 10, which means this index we are going, and up to the length of the length indicates up to 2 power 0, only one element. So you can see 11 having 3 of 10, 10 comma 10. This is how we are building our binary BIT Penvectory. After that, we have to find the searching query, offline queries. If you want the prefix sum of 0 to 5, simply we should go to the 5 minus 1, which means the fourth index. Please go to the fourth index up to the 0. What was the prefix sum? We have to calculate it and we have to return. For this, the prefix sum is done. Similar for everything. If you want 0 to 8, you can go to the respective index 7, and you should calculate all the sum, prefix sum. That's how it works. And coming to our problem, our question is that we are using Finmic 3 and with ranges of 10 power 6 only at max, and because of we compressed, because of we constraints having 10 power 8, and then we are populating with the help of right to left property, going from right to left. Yeah, for example, here we are taking this array, input array, uh, and we have some the compressed array also, like compressed index. Let me take the compressed index this also, where I will be storing here. The first value will be 7. You can see the compressed index at the bottom. I have written 7 2 3 4 7 2 3 4. After that, 165 165. Okay, this is the compressed index. Like we are fitting into this, we are solving on top of this only. We are solving that. We are going from the right towards the left, and we are filling the binary tree on top of this only. We are assigning these values to the given quotient. Not we are tampering the original value, we are taking a distant data structure, store the after compressed value. And here comes we are going from the right to left, and every time we found the value, here you can see that we are traversing from right to left, going from n minus 1, which means the length minus 1, of sixth index go to the respective index of the compressed array, which means 5. Do the minus 1 operation because arrays are zero based indexing. 5 minus 1, which means 4. Go to the 4 and get the count of it and store into our answer. That's how we are building. After that, please consider this element as a one occurrence and update into our BIT. So the 5, it will go here and it will do 5 minus 1 is fourth index. It will go to the respective fourth index and it will flip by using the rightmost that bit and until it goes to the zeroth index. So it will go to this branch, entire branch. It will calculate and this the sum will be stored into our answer. This is where the final structure I have populated, but initially all will be having the value of 0. So all will have a 0. So the first value will be 0, the first result. And if you go to the, if we complete all the solutions, we will form like this the resultant array, binary tree. And let's uh, dry run this. For example, we are taking an initializing an array, the resultant array. We are going from right to left, and we are going to the respect to compressed index value minus 1, and please get the count of it. It will go to the get function of the BIT chemistry, and basically it count, right? We have to take the one variable starting from 0. It will accumulate all the branch. How we are going? Using I, from where we want to start from, nothing but we want to start from the fourth index, and where to go? We are going up to we got 0, up to this condition satisfied. Condition is that less than 0. You should not consider this value up till this. Please calculate that. And every time how we are performing operation, this is where the rightmost set bits come into play. As we want to flip the bit of the rightmost set bit, and we should able to go to the parent of the node. And please calculate all the bit values and store into answer and return that. And that written answer we are constructing in the certain array. And after that we are calling the update function. Please consider one as a count. It will go to the update function here, same structure. Where we want to start from the given index, and here the operation, the perform operation. If you want for prefix sum, we will be passing the previous calculated value, and for this we are counting prefix count. We can pass one of it, so every time it will be passed, and this index will be updating all its childrens by going by updating the rightmost set bit by like stripping back and adding to the respective values, and it will be updated, which means that, for example, if you want to update the 5, the respective below indexes all will be updated. For example, if you want to update 4, the respective index from 1 to 4, all the below branches will be updated. If you want to update, the updation will be done bottom wise, and for summing up values will be done upwards, towards upward. And after forming that, we will get the complete the final binary tree lookless, binary tree lookless, and we can verify the answer as well. For example, 12, right? For 12, what was the compressed index? We have to find compressed index is 7. 7 minus 1 we are doing here. 7 minus 1 get operation. 7 minus 1 is 6. Go to the respective 6 and calculate all its to the parent. We are flipping the rightmost set bits and calculating those bit index, and we are returning that, and we are storing into an answer. The same thing, you can see that we are traversing from here to 0, and we are accumulating everything, every bit index. Here you can see 4 plus 2 6. So the final answer we are getting is 6 for 12, and similarly the following on. That's all. Thank